Nikola, it's great to meet you in person finally. I mean, we've spoken many times, but not in person yet. How's your day going, just to kick off?
It's doing great. Thanks for setting this up. Thanks for having us here for this idea. I think it's amazing just to be able to talk, to meet people in person. It's been going great so far. Yeah. It's been going great. You know, I've been in the RDG and then the International Review Group for 4 years now, and meeting a lot of these people in person.
Maybe you can explain us a little bit why you are in the Netherlands in the first place.
We have the ASME B31.3 Code Week for the first time ever. As we heard on the first day in the presentation, ASME decided to step out of the US and to hold the B31.3 Committee Meeting in Europe because of this, let's say, push by ASME to have more international reach. As a part of this initiative, we have now very good progress in Subgroup N, the international review group, with the participation of many countries, trying to make ASME B31.3, which is already one of the most widely used codes in the world, more accessible or more used internationally.
Yeah, and what is your involvement with the ASME at the moment?
I am in the member of Subgroup N, the international review group, where we are trying to establish the rules and to show the differences between the rules in various countries and how these are applied within ASME B31.3. In particular, when we're talking about Europe, we're talking about application of B31.3 within the PED framework, because we know that PED is something that, well, we have to use in Europe, it's a law. Yeah. And then how do we go about this and how do we use B31.3 within the PED framework? That is well, part of what we're doing. Also, I'm a contributing member of Subgroup B, Subgroup on Design, in which we are discussing, well, everything design related. It's a very extensive group with a lot of responsibility.
Yeah, I think that's one of the bigger groups as well, right?
Yeah, that's one of the bigger groups, and then it's amazing to just be able to meet these people whom I've been admiring most of my life, and to be able to sit down in the same room, to talk to them, to have their takes and opinions, to just, well, at the beginning mainly listen to them, you know, because there is so much of knowledge in there and so much of experience that it's just overwhelming, I would say.
Yeah, that's pretty amazing, and I found it very interesting also to, I mean, you see these you know, industry standards, and you see those names floating around also at the end, to then see, you know, what the system is behind them and meet the actual people.
Yeah, that is made to see how it all works behind the curtains.
Hey, you mentioned the ASME B31.3 being applied in Europe and then having to deal with PED, Pressure Equipment Directive compliance. Yeah. Let's elaborate on that a little bit. Like, do you have any personal experience with that, like ASME B31.3 projects within Europe?
Yeah, absolutely. So it's very common, in fact, to use it, because the PED, being legislation, being a directive, does not impose any kind of standard or code to be used. So we all know if we use harmonized standards like EN 13480, it is easier, it's harmonized. So there is this assumption of conformity with the PED straight out of the box. With ASME, it is not so, whether be it materials, allowables, requirements. So it is very doable. We do it every day, I would say. But still, there are some things that we need to be kind of wary of.
Yeah. What are your experience? You know, maybe you've done a certain project or maybe a certain anecdote. What are things that are challenging when you know, you're dealing with ASME B31.3, you're dealing with NOBOs maybe at some point, you're dealing with PED compliance?
Yeah. So, you know, if we are in category 3, then NOBOs are involved, right?
Category
there is
3, you mean
category 3 in piping, in the PED category 3, yeah, of course. Then we have the conformity assessment procedures. We know that NOBOs are going to be involved, right? Well, not only that, but in general, using ASME may present a series of challenges, you know. Like a common one is, what materials are we using? Are we using ASTM specs? If we are using ASTM specifications and ASME materials, of course, PED requires us to issue PMAs, the particular material appraisals. If notified body is involved, a lot of times this PMA will need to be approved by the notified body.
All right.
You know, it's not a big problem in my experience. We had it done several times, but it is a process. Yeah. It is a process that is required, and ASTM has been trying to make a step forward towards aligning these specifications, but it's a very costly process. It's time-consuming process, and ultimately there might still be differences. So there are some references out there. I think if you just Google ASTM A01 within PED, there are some open documents made by the ASTM committees in which they're discussing a little bit about the property differences, about the composition differences, impurities, and so on and so forth, and the general issues of ASTM within PED.
What would be a challenge to get one of those PMAs, those particular material appraisals, approved by a notified body? I mean, you mentioned we do it all the time, you know, typically it goes smooth. Are there certain topics, let's say you would have a junior engineer come into your team and you would have them do it, that you would highlight like, hey, take note of these items?
No, I think the PMAs are pretty straightforward because there is a template that you can download from the website and just go by it if your company does not have your own, of course. But usually these are established procedures because anybody who is doing this or who has been doing this already have their template of the PMA and how they're going to go about it. The bigger issue could be the definition of yield limit, for example. That's a good example.
The yield limit.
Yeah, exactly, because in Europe or the PED, for austenitics, for example, we are using 1% offset. And that is 81% offset. In ASTM specs, we usually have 0.2% offset at ambient temperature, so we don't have elevated temperature properties. We have one yield, and that's 0.2% offset. So if I apply my safety factor required by the PED to 0.2% offset yield rather than 1% offset yield, of course my lava is going down. But do I have better data? No, unfortunately I don't. With the exception of SA 240, I think, so the 240 stainless steel sheets, which has an option to have 1% offset yield specified. Others, unfortunately, to the best of my knowledge, have 0.2 and that's it.
Yeah, is that only for austenitic steels though?
The biggest impact is there because if you take a look at the labels and the requirements of the PED versus ASME, ASME is typically more conservative for majority of other materials. So for carbon steels, enormous, we have the same thing, the problem does not exist. As we know for austenitic stainless steels, ASME, just because of these differences, because there is so much more capacity beyond the 0.2% offset yield for austenitics, they allow us to go to 90% of hot yield strength or 2/3 of cold because of the testing. So what happens is once the hot properties start to govern, we'll start to see differences.
That's especially relevant for austenitic steel.
Depending on the elongation, of course, we're talking about 30% elongation.
Yeah, and for the other type of steels, you're saying that typically ASME allowables are conservative over the values that the PED requires.
Yes. So there is a very good document by the Department of Energy, I think, by Mr. Antaki. He's an ASME fellow, which provides a comparison between EN 13480-3, which is a harmonized standard, and ASME B31.3, in which he is listing all the differences. And then the general conclusion is that ASME B31.3 for carbon steels and some of the other steels is more conservative because of the UTS safety factors.
All right. What would be other things you would say when dealing with an ASME, let's say B31.3 or maybe any standard, applied in Europe, so having to comply with the Pressure Equipment Directive? What would you say are other, let's say, items or things that you would highlight as something to be aware of?
Well, no, there are a lot of things. I'm a pipe stresser personally, so I'm coming from that field, and I'm mostly worried about the procedure, how I'm going to calculate things, what are the requirements in terms of material levels and these kind of things that we just discussed, you know. One additional issue, for example, that may be presented is the impact test energy requirement, which is quite clear within the PED of 27 joule.
All right, help me out there. The impact test requirement, so that is brittle fracture, if I'm not mistaken?
Yeah, that's exactly it. So the PED requires 27 joule impact test energy, so once you do the impact testing at certain temperature, the measured energy to be 27 joule, right? And due to the differences, and this is also outlined in the document I mentioned a bit before, is that due to the impurities that may exist in ASTM specifications, especially higher phosphor and sulfur content, we may not be able to reach the impact test requirement, the 27. So, but it's not said, you know, sometimes you reach it, sometimes you don't. But again,
so you have to do tests.
I'm not a material expert. This is one of the points I've personally experienced.
All right.
with the notified body involvement, and there was a big discussion. So I do have some input on that. Again, I'm not a material expert, and I can transfer what I read.
How did that end up? Do you then have to do, and in that particular case, did you have to do material tests, or is there another route to solve it?
Well, it's either using material, yeah, you have to do material tests in the end.
Impact test.
Impact testing at certain temperatures, make sure it works, or use low temperature grades. So sometimes you have to change the material.
Any other items come to mind?
No, but when we're talking in general about PED and then the ASME, there was as I said, there is a great push from ASME to make ASME B31.3 book more international. And with this scope, we have the Subgroup N. And Subgroup N last year has completely revised Appendix N. Paragraph N 301, yeah, the Appendix N
Of B31.3.
So that one has been completely revised.
What is that appendix about?
That's about using application of B31.3 internationally. The idea there is to keep developing for other regions, but what we have as of 2024 edition, which just came out a couple of months back, we have very detailed comparison and differences between the B31.3 and the PED. Yeah. So I would recommend anybody who is using ASME B31.3 within PED framework to go and look through that document. It's an amazing piece of work, very, very important, very lengthy process, very thorough, and you should go in and see it.
You mentioned lengthy process. That's also interesting to me. I mean, how does that work to get something? You know, you have some experience. You're doing a deep dive into a certain topic. In this case, the application of ASME B31.3 in the PED framework. How do you go from looking into it and discussing it with people to actually having it incorporated in the B31.3? I mean, you mentioned lengthy process. Maybe you can elaborate a little bit.
Well, it's hard. When you join the code, you start talking. Everybody is amazingly nice in the code committees. So whatever idea you may have, you may put it forward. You may discuss on it, see if it's worthwhile to go through with it. Yeah. If it's a good idea, you start working on it. You get assigned your action item, your tracking number, everything that needs to be assigned, and then you're going through the process, and then you are discussing with the group in meetings like this, the progress, what is happening, if you need somebody's help. You talk to people, you get it done, you send it out for balloting, and then you take it from there. Then you get comments, additional comments, negatives, replies, Personally, I'm just starting out with this process, so I'm not the best guy to be telling you this, but there have been people, I have seen the process, I know what it takes, but it depends. It can be lengthy, it doesn't have to be, but in my experience, we are all doing this this is volunteering work. So this is volunteering work, and then it takes time. You have to find time. You have to make time to do it. And that can take some time, especially if more people are involved. So right now, for example, I'm working on the proposal to include an PED compliant example within the Appendix S, the example section of ASME B31.3. And there I needed to involve other people because we needed to do different software for pipe stress to align the results. And of course, people have to find time to do it. And I've been talking to people from Europe, people from Houston, people from the US. So it's kind of a joint effort. But then again, we have the time differences, we have everything we have to circumvent, we have to solve. People are working, so they have to find time. It's not always easy.
But so if I understand you correctly, the ambition there is to have, Appendix N describes the differences, to apply ASME B31.3 in the PED framework, you want to have a worked out example of that, challenge.
Exactly. With a special focus on the austenitics, like we discussed just now. Just because this may be a big pitfall, right? And it's not always said that more material is better.
It's not always said that more material is better. I know that from a brittle fracture failure point of view.
From a lot of point of view. So if you think about it, what could happen if you lower your basic allowable stress? So you take your first commercial size and now your difference may be becoming bigger, right? What happens is that, of course, thicker pipe.
Stiffer system.
You got it. So you have more loads on the fixed points, on the supports, you have higher expansion stresses, so expansion stress range. So all this impacts. So for example, if we increase the allowable stress or we decrease the allowable stress, we increase the thickness. And if this system was operating, let's say at the margin at 90% of its allowable, you may push it just over 100. So we are trying to use thicker pipe, but we are inherently making it worse for fatigue. Or cycle coding.
So it's important to know the nuances there and not just think, I'll make everything thicker.
I would go a step further to say that it's getting more and more common in the industry to see these things, just adding layer upon layer of safety, which may sometimes lead to over-engineering in the best case, in the worst case, lead to unsafe system.
Yeah.